is Ira Pastor. I am the Aging and Longevity Ambassador for the ideaXme show, highlighting thought leaders, the big thinkers for the ideas of the future and tomorrow. And we have a really exciting show today. Aging, as we talk about it, is an extremely complex process that is controlled by a series of nested hierarchies that expand from the very small, their genes, proteins, gene regulatory networks, on up through more complex physiological regulatory networks, bringing in forces of mechanotransduction and membrane potentials, hydrodynamics, tissue tensegrity, and then of course sort of beyond the body into sort of the organism's complex microenvironment. Today, we are going to take a bit of a journey to another level of this hierarchy, to something that we'll broadly call the macrobiome. Now, while many in the public are familiar with biotech terms like genomics and proteomics and monoclonal antibodies, there are other terms that they may be less familiar with. Ectocrine dynamics, interkingdom signaling, semio-chemical communication, induced phenotypic plasticity. A lot of these are sort of really complex ways to talk about basically one thing: how living organisms of one species can signal and affect the health and wellness in a positive way of another species. And today we have a fascinating guest that is really in the epicenter of this. Today we have Dr. Jose Santiago Mejia. Dr. Mejia is a medical doctor who spent the last few decades working in the area of infectious disease, immunology, parasitology, studying a wide range of disorders, including malaria, Chagas disease, leishmaniasis, and really spanning a wide range of human pathologies. Yet, interestingly today, as we get into this topic of the macrobiome, paradoxically, one of the species that we're going to be focusing on in discussion, the common mosquito, which nowadays goes down as one of the most deadly organisms of the planet and responsible for 750,000 deaths around the world, may very interestingly, paradoxically, hold biochemical and pharmacologic secrets for addressing disease and beneficial applications in hundreds of millions of patients around the world. So with that brief introduction, welcome Dr. Jose Santiago Mejia to the show.
Thanks a lot, Ira, for the invitation, and thank you all for staying and attending the discussion, because I believe that this is really something that needs to be debated, given that, in my opinion, the scenario that I'm going to be describing is essentially a catastrophe, slow-moving catastrophe, because some of the interventions that we are implementing to control some diseases are essentially seeding the ground for a much bigger problem. And I will give you some details about this as we go along during the interview.
That'll be great. But let's start out with you. Typically, we hand the mic over at the beginning of the show, give you the floor, just to talk a little bit about, who you are, where you grew up, how you got interested in science, how you got interested in medicine, how you got interested in parasitology, just a little bit about your background that I'm sure the audience will find very interesting.
Well, I am originally from Medellin, Colombia. Ever since I was my childhood, I was essentially very curious and I love to read, and very early on I realized that I had a interest mostly on what is not known, and so that essentially I structure my learning process based on that perspective of looking for the unknown in one particular discipline, so that I decided to get into medicine, not because I wanted to essentially treat patients or be a surgeon, but rather because I realized that there were too many questions that needed to be addressed in the field, and it was essentially a fertile ground for for research and the kind of interest that I had in those days. And so I enrolled in a medical school in Colombia. I studied there for 7 years, Universidad CES in Medellin, and then after that I had the opportunity to work in the laboratory of a very well-known scientist in Colombia, Patarroyo, and in Bogota. He was developing at the time a vaccine against malaria. So I got into learning everything about the parasite and then the vaccine development. In those days, I was actually beginning to train to be a rheumatologist, but then Dr. Patarroyo sent me to the jungles of Colombia looking for patients with malaria. And then at that point, for me, that was really the turning point in my perspective about life, because I was able to see the misery, the miserable conditions and the poverty, abject poverty in which the communities, Indian communities and Black communities in the jungles of Chocó and Amazon were living. And at that point, I committed myself to work to solve problems on the neglected tropical disease arena. And so I changed completely my focus and I started chasing ways to actually help. And then in doing so, I went to Mexico to study on one other disease that is a very serious problem, neglected disease with amoebiasis. And I started to learn about the antigen vaccine development, experimental models. Very similar approach to that of the one that we were working with malaria. Then I received a postdoc offer from New England Medical Center in Boston, here in Boston, and then I had the opportunity to work yet with another different parasite that is as well neglected, and it is Chagas disease, which is the only totally Latin American disease. It only occurs in residents from Mexico all the way down to Patagonia, but nowhere else on the planet. And it's transmitted by a different arthropod, the kissing bug. And so the need for a vaccine also was very clear. And I studied precisely characterized antigens and trying to figure out which will be the best candidates to do so. Then I received an offer for a second postdoc position in a biotech company in England Biolabs in Beverly, Massachusetts. And this time I was working with a much more complex and more difficult, more challenging parasite, which is the filarial parasites. These are also cause for very serious problems all around the world, and also they affect the animals as well. And so I started working with a series of parasites, group of parasites, filarial parasites that are transmitted by mosquitoes. The same mosquito that transmits dengue fever, for instance, is capable of transmitting this very complex worm. And it's actually a fascinating story, because it turns out that the larvae, the infected larvae, just stay dormant inside the infected mosquito. And then they sense that the mosquito is taking a blood meal, and at that point they crack open the head of the mosquito, and they migrate out of the mosquito and get into the wound, and that's how the infection process takes place. It's one single little worm, and it gets in, and then it essentially migrates to your tissues and mature, begin to lay eggs, and then all these different diseases, filarial parasites, have the very same life cycle. So. But then again, once again, I was chasing the antigens against the parasites, and it proved that it's just impossible. And it turns out that, I had a third postdoc in Colorado this time, and it was on a different parasite, also transmitted by a different arthropod, a sunfly. It's Leishmania parasites. It's a very serious problem that is getting really worse all over the world. And then it turns out that they had a completely different set of antigen systems, evasion mechanisms. So it's extraordinarily challenging. I had a unique opportunity to see the problem of vaccine development from a very different perspective. And in the process of doing so, you begin to feel frustrated, because none of these vaccines to this day do work at all. There's no malaria vaccine. There's no vaccine against Chagas disease or filariasis or leishmaniasis. And then I met Dr. Richard Titus, who was the pioneer of a new approach to the diseases. Who told me, listen, why don't we work with a new approach that is to develop the vaccine not against the parasite themselves, but against component in the saliva the arthropods deliver at the right site along with the pathogens. I was taken aback. For me, it was a revelation. I was not even aware that a mosquito could salivate. And so it turns out that all of these macrophages arthropods actually do need to actually develop a very peculiar cocktail of salivary molecules in order to be able to steal the blood of vertebrates. And in doing so, it opened a page in my book that I have dedicated my life to study arthropod saliva and the biological underpinnings of its function and its potential in both in the context of infectious diseases and, as I will mention perhaps later, in the context of chronic non-communicable diseases.
And this is really, a fascinating background to the next part of the story because, you were involved in these different research paths, dealing with, as I said, a lot of nasty organisms, a lot of quite infectious microorganisms. Yet you then publish in 2014, as you were just mentioning, when you changed your focus, or you had this additional focus on saliva, and a wonderful paper entitled Arthropod Saliva, the Missing Piece of the Hygiene, Health, and Disease Puzzle. And I like, coming out of the pharmaceutical industry, I love pharmaceutical history, and sort of, I point to the fact that most of the greatest discoveries that ever occurred in this space, were not simple things that happened in the lab, but were these, either accidents or these eureka, aha moments that, wow, let's look at something a little differently, and it potentially opens up a whole new pathway. And so, just, I'd like you to talk a little bit about your aha moment as you had this realization that, there's something here. Once we separate the nasty stuff, there is this potential treasure trove of other things present that the scientific community probably should focus on. And also simultaneously, if you could talk a bit, because your paper not only mentions sort of this diversity or this biologic diversity that we are missing, but also from some of your experience in the jungles and in some of the endemic regions of the world where you have these organisms, some of the paradoxical things you saw between endemicity and chronic disease. So if you could speak to a little bit about this sort of aha, eureka time in your career, that'd be great. I think the audience would really like it.
All right. So yes, when I started working with the idea of targeting the saliva of the mosquito of the parasites, then I immediately realized that there was a huge opportunity, because it turns out that then at that point it was then theoretically possible to talk about a pan-arthropod vaccine. You see, a pan-arthropod vaccine will be one that is one single vaccine to prevent every single disease caused by these vectors, from dengue to malaria, everything. So it was a extraordinary opportunity that needed to be addressed and at least looked into. And then I dedicated about 8 years looking into this, trying to figure out which will be the targets, potential targets, and then evaluate each one of them in experimental models. And at that point, I was working with 3 different species of different vectors and 3 categories and 80 species, and trying to essentially pinpoint, identify those that are highly conserved across the different arthropods. And then in the process of studying the possibility of peptide segments, then I realized that the clue was in the glycans. You see, the thing is that each one of these, one of the fascinating things about all this, going back to your comment about pharmacology, is that each species of arthropods, and remember, arthropods are the most diverse taxa in the biosphere. There are more than 1 million species, and many of them adapted to a blood meal type of diet, and so they had to adapt over eons and eons to the changes in their mouth parts and in the saliva to be able to essentially neutralize many of the whole defense mechanisms. All of them actually has to be anticoagulant, vasodilatory molecules, anesthetics, immune modulatory molecules, and so that only by developing this formulation of sorts, it's a complex formulation then they will be able to neutralize something that is characterized by its intrinsic redundancy. So that is why it was so crucial for the mosquitoes in their development. It was to develop a complex mix of molecules that simultaneously will inhibit and deactivate all these physiological defense mechanisms at once, at the same spot. And that's very crucial because that will bring us back to a discussion about applications in disease control, this issue of redundancy. But in any event, at that point, I was looking to options and initially looking into peptides that were similar. But then I learned that it turns out that from a protein perspective and gene perspective, the saliva of a tick is extraordinarily different from that one of a mosquito or from a lice or from a flea. Each particular arthropod group, taxonomical group, and even species develop their own recipe. And so going after the proteins didn't make sense for the purpose of the pan-arthropod vaccine. So then I switched into the glycan story. And just for the people that are not very familiar with this, there is a cellular structure that's called the Golgi complex that take proteins and then put some sugars in the process of secretion of these compounds. And so then I realized that that was the target, because it turns out that the Golgi system of arthropods is trapped into an evolutionary, essentially, a dead-end street. It never was pushed to develop as complex as the one that was a mammalian structure. So voila, that was the ideal situation, because not only those structures were very primitive, but they also were very immunogenic. And so I started working on immunity against both of them, the N-linked and the O-linked glycans. And we developed a very interesting system to evaluate those. We developed something that is called the Bioquark tissue platform, which is a vaccination platform in which we essentially assess the effect from an inflammatory perspective and in vivo situation. And so the idea was that after, as I say, after evaluating several systems, we realized that it was a fundamental problem. And that is that these sugars, actually, they induce something that is has been very well characterized. It's what is called a Th1, Th2 bias of the immune response. And so in essence, it changes the nature and the character and the strength of the immune response at the bite site. And that makes perfect sense, because essentially that's what the mosquito wants to do, is essentially to deactivate the defense system of the host. And they have essentially optimized the system for that. But it turns out that that has been linked with allergic reactions in humans. And so when I tried to get the funding, the grant funding to pursue this further, essentially it was totally blocked, because the argument was, well, you're going to be developing a pan-arthropod vaccine that induces allergies. How do you expect us to fund something like that? That monstrosity. So that for me was a frustrating situation, but at the same time, I mean, I'm a fighter, so I just wanted to understand more about this. And well, it turns out that my previous experience with nematodes, because also in Colombia I worked with other type of intestinal nematodes and trematodes. Then I knew that for instance, there's a parasite, Schistosomal manzoni. It's also very prevalent in the world. There are more than 200 million people who are infected in Brazil and India and other tropical areas. These worms, they induce a similar reaction, eosinophilia in the liver. And it turns out that I have worked in the past with one of the leaders, Dan Harney at Harvard University, on the molecules that are responsible for that. So I wonder, perhaps I'm going to follow his protocol and see if also happened with the mosquitoes. And it was totally shocked to realize that not only mosquitoes, ticks, and 3 different groups of arthropods were working with the same molecule that is used by trematodes to deactivate the immune system, and that are responsible for an eosinophilic response that actually effectively deactivate the defense system, allowing these parasites to live a long life inside the host. And then that is an striking example of convergent evolution, and that was crucial, because at that point, then I realized, wait a second, not only this may be a problem for the issue of vaccine, the development of pan-arthropod vaccine, but perhaps more importantly, the idea that arthropod saliva might be linked with something that has been also been in the discussion for some time, which is the issue of the hygiene hypothesis. And in the hygiene hypothesis, essentially people have realized that perhaps, or just from a historical perspective, the countries that were able after the Second World War to implement very effectively sanitary measures that eliminated parasitic elements from the environment, they now are essentially suffering an epidemic of chronic disease, diabetes mellitus, multiple sclerosis, and a variety of diseases that were not even in the radar in the 19th century. So then suddenly a Scottish physician made the link, and he began to propose that there was a link. The hygiene was a pathology, and then I realized that. Given that the mosquitoes were doing the same thing that the nematodes were doing, and in the context of the hygiene hypothesis, there was the possibility, theoretical possibility, that we needed the saliva of arthropods for something physiologically. And so that's essentially the fundamentals of that paper that you mentioned. But now, after continuing researching this, I essentially came to another critical point in which there was essentially a linguistic switch in the whole argument, because up to that point I was arguing, essentially saying that exposure to the saliva of arthropods is good for humans, for human health. I want to make this very clear. Exposure to an infected mosquito is always bad news, and I am not advocating that we should be bitten by them. So we should kill them. But what is really tough question, and we don't have an answer for that. Nobody has really been studying this consistent systematically. Well, how about being bitten by a healthy mosquito? Is that good or bad for us? So at that point, I was arguing that is actually good for us. Why? Because these mosquitoes produce these anti-inflammatory molecules, all these anticoagulants that may help us in our homeostatic system.
Well, let's dive a little deeper into that, because that is a fascinating background, but it is also sort of integrally connected, because as you mentioned, obviously you took us back in history to World War II, but now bringing it forward a bit. There was this you probably saw it, of course, but there was a recent paper out of University of Queensland down in Australia about sort of the expected decline in so-called entome of fauna predicted this century, which, it's predicted, something like upwards of 40% of insects are potentially going to be gone. And we're just talking about a few. And obviously the general public is, knew a couple of years ago what, the catastrophe when the honeybee decline, and, these little, and I totally agree with you. While there are groups out there like Gates Foundation and Google and such that are, trying to eliminate certain species from the earth entirely, and we're not opposed, obviously, to getting rid of the ones that carry the nasty organisms. At the same time, we have to realize that if they're all gone, and we miss this opportunity to tap into the wealth of pharmacologically active stuff that may be there, we're going to miss a major opportunity. And so, I wanted to sort of use that topic to transfer a little bit, take off your scientific hat for a moment, or one of your scientific hats, and let's move into the sort of pharmaceutical development realm for a moment. And think, you mentioned painkillers, you've mentioned anticoagulants and immunomodulators. In your paper, you mentioned neuropeptides. Just talk a little bit about, obviously drug development is a long process, it takes time. I come out of the pharmaceutical industry, as you know. Talk about some of the potential classes of sort of pharmacological agents that you see potentially isolating from the saliva of, whether it's mosquitoes, whether it's other organisms. What are just some of the basic classes that you may see as sort of good paths to follow with what we know today?
Yes, there's a group at the NIH directed by another pioneer, the first experiment with the mosquito saliva, or actually sandfly saliva, that Dr. Titus conducted was with Jose Rivero, who has been actually working for now, since 1982, essentially characterizing the saliva of every single hematophagous arthropod on the planet. And essentially, they have the whole catalog of molecules. All of that information is available through NCBI if any of you wants to dig into it. It's a fascinating work. And essentially, they have Dr. Rivera is a pharmacologist himself. So he has been essentially pushing some of the candidates that he has identified in some of these species. So there's an ideaXme, or there's XLR is the genetic coagulant, and so forth and so on. But going back to your question, the idea is that pharmacologically, it's a treasure trove, essentially. There are hundreds of potential molecules in that pipeline that could have be proved as useful, for instance, as a uridine, which happens to be an anticoagulant from leeches that now is available for clinical application. It has proven very effective. And that brings us back to about something that is essential about biology, and that is that given that these mosquitoes evolved with us for so many generations, there's a coevolution process. They were capable of optimizing from a molecular perspective these candidates, these pharmacological agents. And then, so essentially, the best anti-inflammatory molecules on the planet, you can bet that they will be present in these mosquitoes or in ticks, because they have been proven to be very, very effective. And so that makes it very enticing to work with them. And actually, as I said, the group of Dr. Rivero is actually working on anticoagulants, inhibitors of the complement system, with application, for instance, in transplant biology. Also, there are vasodilatory molecules, and those are actually considered for treatment of patients with anything from myocardial heart attacks or stroke problems or peripheral blood disease. And so each one of them has the variety of application. Now, there are the neuropeptides, and that is really a fascinating story that I've been personally very digging into it quite a bit lately, and that is that there's like this cloud of peptides in the saliva, and many of them are not really clearly what the biological function is. I work with one of them, maxadilan, which happens to be a vasodilatory molecule, and interestingly, it has a receptor in the pituitary gland. And so you just think about it. There's a molecule in the saliva of some fly, and that molecule produces strong vasodilatory reactions. And in addition to that, it binds to the pituitary gland. That begins to connect things. And that's the thing, is that going back to your reflection about axis of connection, interactivity, the physiological networks. And so that, yes, there is essentially a long list, a catalog of potential pharmaceutical agents. But I just want to essentially throw in the perspective. And that is that perhaps we should consider changing our perspective to mosquitoes, especially if we can guarantee that they are healthy, that they do not transmit a pathogen.
Absolutely.
It is the following, is that a mosquito can be seen as an industrial platform. So instead of being a problem, it can be part of the solution, the critical element of the solution. And just think about that perspective for a second. It turns out that a mosquito knows how to produce the cocktail molecule that you need, and in the right dose, at a very low price. You don't need extensive training or technology or a special facility. You can build one of these facilities in any poor country, even if you don't have electricity, and then you can begin to operate essentially a unit with that perspective in mind, medical interventions through saliva.
That is a it's a fact. Not only the topic of sort of the evolutionary perfected cocktail, which I'm a major proponent of, having my own sort of background history in the area of phytochemistry and knowing sort of what these different biologic kingdoms have created over hundreds of millions of years, in comparison to what we've been doing the last 100 years in the world of synthetic chemistry. But you're bringing up a very interesting topic I want to get into next, because a lot of the audience will, while they're familiar with traditional drugs, one thing that is a lot less well known is that, and this is in the United States here, the FDA in the past several years has approved many what we'll call living organisms as therapeutic entities. So, it strikes many as fascinating that you talk about leeches, but leeches, maggots, and helminth worms are all approved in the United States by FDA as medical devices for various conditions, Crohn's disease and skin ulcers that don't heal, due to this very process of saliva and spit having this wonderful pharmacological cocktail of stuff. And so, yeah, if you could briefly just, talk a little bit, because, aside from all of the research you've done, you've also been at sort of the forefront of the sort of the breeding picture as you've done your work. Talk about just a little bit about, what you might see. Okay, on one hand, we have the ability to isolate these pharmacological agents for sort of one particular area of the pharmaceutical industry, and find new painkillers, anticoagulants, and autoimmune modulating substances. But on the other hand, there is the living organism, which you rightly say has been here several hundred million years. It's been biting everything along the way. It's evolutionarily optimized as a beautiful drug delivery system. So, like the leech and the maggot and the helminth, do you see possibilities in the future as developing, clean mosquitoes as the therapeutic delivery vehicle themselves? And just, you could run with that a little bit, but it's something we've discussed offline, but I'm sure the audience would be quite intrigued to hear about your ideas.
Yeah, well, actually, yes. The people have actually published, there's initial literature about the idea of actually using mosquitoes as a platform to deliver vaccines. So essentially to introduce the vaccine in a mosquito, because just think about the mosquito is an ideal delivery vehicle for parental pharmacological agents without pain. And again, you don't need the stability of a shelf life evaluation process that you will have to face with the traditional pharmacology, and especially with vaccines. There's a lot of issues about the adjuvant effect. There's a disease already recognized, a syndrome actually that is induced not by the vaccine itself, but by the adjuvant that is made with the vaccine in order to boost its efficiency. So that having a platform like this that not only is able to deliver at low cost and high efficiency a pharmaceutical, in this case, a heterologous molecule that's introduced into the genome of the mosquito, then that will be ideal. And so thinking as I knowing you as somebody that is very interested into the future and essentially fitting to the philosophical underpinning of this platform, I can see that in the future with the human colonies are in space, they are going to bring mosquitoes because they are essentially very, very maneuverable, flexible, and at the same time versatile tools for a variety of applications of their own based on what they naturally produce, but also because we can engineer them to produce some additional stuff for us.
Fascinating. It's truly a fascinating. When you talk about, beyond the Earth, and you think about all the things that they're bringing up on the International Space Station nowadays to see what happens, whether it's salamanders or flatworms or tardigrades. I think I agree with you on that. That probably mosquitoes should be in a payload at some point, because rightfully so, if they're connected to so many integral biologic systems, and we head off to Mars or elsewhere, we really need to think about sort of the, as I said, the macrobiome to what's keeping us healthy. So this has been exciting. But right now, as we on this show, we like to transition from science to what we'll call the science fiction realm, and we throw this question out to everybody. Dr. Mejia, if I was to pull a time machine out of the closet here and allow you to use it, you can go anywhere you want. You can travel to the past. You can travel to the future. We'd just like to hear from you. Where do you want to go? Who do you want to meet? and what are you going to talk to them about? And have the floor with that one.
Well, first of all, I have to explain that while I was in the medical school in Colombia, there was the years of essentially of civil war and the drug trade. The two things together was a terrible cocktail. So there was so much violence. I saw so much blood. For me, it was a shocking experience. It was very revealing about the human nature. So for me, the issue of violence have been always very strong. I have some motivation in my psyches and in my philosophical tendencies to understand and study humans as a species. Not as an individual, but mostly as a species. And in that note, there's something I would love to be able to go and have a chat with Jesus Christ, if possible, to ask one question that has to be presented with the issue of violence. Because you see, I am intrigued by the fact that he was sent to Earth, and why the Middle East? Why Belen? I mean, we had a lot of places that were turmoil, there was violence, decadence, the poverty all over in those days. And so, was there any particular form of violence that essentially cut the eye of, I don't know, of God, and then essentially decided to send it precisely to that point to intervene? It's an intervention, a planetary intervention. And then I was just thinking about it, and I figured, well, I have an hypothesis, and I would like to put it forward to Jesus Christ to see what he has to say. And is that there was this unique type of violence that, in my opinion, is absolutely revolting, the worst that I can imagine, and that is to essentially offer and sacrifice the first sons, and that which was a tradition in those days in Belém and through the surrounding area. And I wonder if that actually caught the eye of God and essentially decided to intervene because that was too much. And then essentially Jesus Christ was sent to make a transition. And actually the fact is that he accomplished the feat very effectively because his sacrifice managed to essentially drive the cultural transition from the physical act of killing a human being to the essential transition to a symbolic killing that was mediated by him. And that's how I interpret, by the way, the sacrifice of Jesus Christ in the context of social intervention strategy.
Really a pleasure having you on the show today. After the show, we will put the video live. We will, on the ideaXme site, we'll have a link to Dr. Mejia's dozens of his papers, scientific literature, more on his background. They can visit, and the interview will, of course, will be up on YouTube and various other platforms. You know, we hear so much in today's scientific world about sort of the reductionist view in the very small, but, you know, taking this much larger holistic picture on the grander system is truly fascinating. I think the audience will really appreciate that. So, Dr. Mejia, thank you so much for joining us today. This was a major pleasure.
Thank you.